Thank you. Lighting. What's the time now? Oh, okay, thank you. Chandra is not here. Okay. Okay, so he asked me to start at 1:30, which I think is right about now. 1 minute, okay. This is not very sensitive. Okay, so folks, welcome back from the very nice lunch. And so I guess what we want to do for the remainder of the talk is basically just to survey some results in this area of second asymptotics. The first part, the first 3 hours was really the fundamentals. What I hope you can take out of the talk, and some of the techniques that are used, right? In particular, the central limit theorem, the evaluation of the information spectrum divergence, and how hypothesis testing plays a role in channel coding and lossless source coding. Okay, so those are really the fundamentals. Those techniques results were already present in Strasson's paper in the 1960s. So I hope I did a reasonable job in trying to convey some of the information to you in a way that is understandable in today's language of information theory. So as I mentioned, in the rest of the talk, I want to cover some of the more recent results developed by myself and my collaborators, okay, in which we study various multi-terminal systems, and we try to look at the fixed error probability asymptotics. That means that we try to look at second order expansions. The first class of systems that we look at are channels with state, followed by Slepian-Wolf coding, followed by simple classes of interference channels. Okay. All right, so channels with state. What are channels with state? Well, a channel with state is one that is not only influenced by the input to the channel, but also a random state. This state evolves according to a probability distribution of S. So now, in the study of channels with state, the state can be deterministic, it can be random, it can be available at the encoder, it can be available at the decoder, it can be available everywhere. All right? So in this part of the talk, I will only focus on two situations. The state is available at the decoder, and the state is available at both the encoder and the decoder. In some sense, this is the simplest. These are the two simplest scenarios. The situation where the state is the random state is only available at the encoder is called Gelfand-Pinsker problem. And for that, we do not have conclusive results on the second order asymptotics. We have some results, some partial results, and today, I'm not going to talk about partial results. I'm going to talk about conclusive results. That is, we have achievability bounds and converse bounds that match. Okay, so this is perhaps the simplest model in which the state is known at the decoder. Okay, so we have a channel W is assumed to be discrete and memoryless, so the state sequence is also discrete. Okay, the input is discrete, the output is discrete, okay? Everything is finite. The state is stationary and memoryless in the sense that the state is an IID, P of S is an IID distribution, okay? Okay, so it evolves in this very simple fashion. Okay, now we can ask the same questions. What is the capacity? And what are the second-order terms? Okay, so the capacity is well known. The capacity of this channel, which is dependent on the channel, as well as the state distribution, is this conditional entropy, okay? Where the maximization is over the input distribution P of X. Now, how do we see this, okay? Well, this is really simple. We regard the output of the channel as a vector of two elements, the output of the channel Y, as well as the state, right? So you can think of the channel as W tilde, Y and S given X. And the output of this channel is, the input is X, the output is the vector Y and X, S, okay? And by Shannon's theorem, we know that the maximum achievable rate is I of X to YS, okay? This vector YS. And by the chain rule of mutual information, we can write this mutual information as the conditional plus the marginal. And this term drops out immediately because the message and the state are assumed to be independent. I didn't say that, but it's true. And so we recover immediately the conditional mutual information. And another way of saying this is that the normalized logarithm of the total number of code words, the maximum number of code words we can transmit across this channel with state, is that this particular expression up here. So the only thing we can control is the optimization over, is the input distribution P of X, okay? And the strong converse holds is quite easy to see because it's exactly equivalent to a DMC, okay? So this statement holds for every epsilon between 0 and 1. Okay, now we can ask the same type of, we can pose the same type of question. What are the second order asymptotics, okay? And this was derived by Ingber and Feder in 2010. This is not so difficult. So let W sub S be the channel indexed by the state S. So that means that WS is a channel from X to Y, and it is indexed by state S. You fix the state, and you look at the channel as a mapping, a stochastic mapping from X to Y. Okay, and assume that the information dispersions are all positive, all right, for every S. Then we have this asymptotic expansion, which looks remarkably like channel coding. The first term is, of course, the capacity of the channel, and the second term is the dispersion, okay? But I owe you a definition for this V. What is it? Well, the dispersion above, okay, this V term here, can be written as the expectation over the state of the information dispersions plus the variance of the capacities, okay? So this part here is representing randomness of the channels, okay? Each channel has some randomness built into it, and that is represented by these V's, okay, that we talked about a lot, all right, before the break. And these are capacities. These represent the randomness of the states. There is some variance over the states. So this is very nice because a channel with state has two sources of randomness, the channel itself as well as the state. And this is built into the definition of the dispersion for this particular channel, which is influenced by both the channel and the state. Now, we can do a little bit of calculations to convince ourselves that this is true just by regarding the channel as a stochastic map from X to the vector output Y comma S, all right? So I defined this new channel W tilde, Y and S, X. And we have seen from the previous definitions that we should be concerned with the variance of the log likelihood ratio, okay? So just by doing some simple manipulations, we see that we should be concerned with log of W tilde and the input distribution multiplied by W tilde evaluated at the vector output, okay? So now, from the law of total variance, you know what the law of total variance is? Total variance, you can decompose it into two parts, expectation of the variance, variance of the expectation, okay? Then we get exactly what we were looking for. This represents the randomness of the channels, the average randomness of the channels. This represents the randomness over the states, okay? So this is very natural. And this is perhaps the simplest possible illustration that some of the results that we have developed in the second part of my talk let's carry over in a very natural way. But this is a really, really simple model because we simply have to regard the output Y as a vector output Y comma S. Okay. So this is the simplest possible multi-terminal model, and it was developed by Amir Ingber and Merfeder in 2010, right after the publication of the Polyansky-Poor-Verdue paper. So that was a nice application. What is perhaps not so obvious, all right, is when we have state information also available at the encoder. Of course, we can do better. Capacity is higher in general, right? Now here, the state sequence Sn, think of it as Sn, is available at encoder as well, all right? So we will assume exactly the same things. The channel is discrete membryless. The state sequence is in a stationary and membryless way, IID, okay? Now, the capacity of this type of model is very well known, okay? And by a time multiplexing argument, we can show the achievability of this quantity. What is the difference between this quantity and the one that we show? Now, there is a conditioning on S. So we are optimizing over a bunch of input distributions indexed by S. Okay? So observe that in the past, when we only have state information available at the decoder, we optimize over P of X, input distribution. Here we are optimizing over the conditional distribution of X given S. So we are in fact optimizing over cardinality of S input distributions. Essentially, we can also code according to the state that is available at the encoder. So how do we prove this? This is an exercise. This is a statement even. This is a statement in El Gamal and Kim's book. All right. And the argument is very simple. All right. So here I changed my notation of the message to J. Okay, I should have been consistent. It's called M. So we split the message into a number of components. We split the message into how many? Cardinality of S components, independent parts. And each of the messages is 8RS. Okay, RS sums up to R. Now, we ask ourselves, if we fix a P of X given S equals to S, all right, by Shannon's channel coding theorem, we require mutual information of X to Y, condition on S equals to X, S, all right, this conditional mutual information, conditioning on this event to transmit the sub-message JS reliably, okay? Now, once we average over the state, we get that any rate below conditional mutual information, now we have already averaged over the state, we can transmit this amount or slightly below reliably. So that is essentially the proof, the direct part proof, the achievability proof of this capacity result. So we basically split the message into many parts, cardinality of S parts, and we use a reliable channel code to transmit that sub-message, okay, across the channel. And for that, we need this, all right? Then we average over the state, and we're done. That's the definition of the conditional mutual information. Finally, we can optimize over PS, and that results in that particular expression. Okay, so here we have more freedom. We have the freedom to code according to the state, roughly speaking. And we can ask exactly the same questions, right? What are the second order asymptotics? For this, it's not so trivial. Okay, and this is due to myself and this handsome gentleman here, Marco Toma Mitchell, my collaborator over the past 2 or 3 years. Okay, this last year in IT. So again, we will assume the same things. The channels are membryless, and the channel indexed by the state S is well behaved in the sense that its information dispersion is positive. Okay, so its information dispersion is positive for all S in S. Then we have exactly the same type of expression, okay, as before. All right, so the dispersion consists of 2 parts: randomness due to the channels, randomness due to the states. Again, it's very natural because there are 2 sources of randomness in this system: the state as well as the channel. All right, so this is very natural, but it requires a more intricate argument to prove this. Requires a slightly more intricate argument. Okay. So as I mentioned, proof of this theorem is more involved than the case without the state at the decoder, at the encoder, because we can't regard Y and S as a vector output anymore. At least it's not so obvious. Huh? You can, but it won't help you. You can do better, right? So it can't help you in the converse part. So we need to modify the time multiplexing argument I showed you just now to achieve capacity, such that it is also dispersion optimal, such that it's also second order optimal. And that's far from obvious, at least to me, you know. So I will try to sketch an argument, okay? I'll try to sketch a proof, a proof sketch, okay? I will try to show you that this expression is believable. Okay. Obviously, I don't have time to go into all the details, but to do that, let us consider two simple quantities. This is called the empirical capacity for a given fixed state sequence. Okay, this sequence is discrete. Okay, it's a discrete sequence. We can consider the average over all the capacities of the channels indexed by the state Si. Okay, and we can do the same for the dispersion as well. Okay, so each channel has some dispersion, and we can take the average over all possible dispersions indexed by the state Si. We call that the empirical dispersion, and we call this the empirical capacity. So it turns out that, if S is typical in some way, if S is typical in the usual strong typical way, okay, then what we have is the following. Let me try to help you to understand this little expression. This is the optimum error probability for transmission of information across n users of a memberless channel with m code words when the state sequence is fixed to Sn, little sn. Okay. Now, if the state sequence is the same for each Sn, then this is a discrete memoryless channel. If it is different, we have a memoryless channel only. We don't have stationarity. Okay. So one can show by extending some of the arguments that we made just now that this optimum error probability behaves also as a Gaussian. Okay, where the term you subtract, the capacity term, is this empirical capacity, and the dispersion is the empirical dispersion term. Okay, so this is a simple generalization. Okay, an inversion of this quantity that we spent a lot of time deriving in the second part of the talk. Okay, so if you basically flip this around and make epsilon the subject of the formula, all right, you see that you recover this this expression here, all right, and all the s's are the same. Okay, thus, what we need to do and to analyze for random states is the expectation of this phi function, expectation of the cumulative distribution function, where the expectation is taken over the state, right? Because here the state is fixed to little sn. Now, if we want to analyze a random scenario, we basically take the expectation of this leading term over all possible choices of the state. So this is an expectation of a phi function, expectation of a cumulative distribution function. How do we simplify this? So we were stuck here for maybe a few weeks, and we made some progress, okay, to simplify this in terms of one single phi function. So this is an average over a bunch of cumulative distribution functions. So how do we simplify this in order to get a very nice expression with a nice dispersion term that matches my theorem? Okay, so here we require two technical lemmas, the first of which we won't prove, the second of which we will prove halfway. All right, so basically, as I mentioned previously, we need to approximate this quantity here. This is an expectation of a phi function. M is the total number of words, the code words. This is the empirical capacity and empirical dispersion. So the first thing we did was approximate the empirical dispersion by the average of all the dispersions across the state. So, and the following we can prove using some tools, okay, using some very complicated tools. We can show that the following holds uniformly in alpha. So by uniformly, we mean that the remainder terms, if I take this, subtract this, the remainder terms do not depend on alpha. Okay, so I effectively replace the randomness in the denominator here with a deterministic quantity without too much loss. The second part is perhaps more interesting. Next, we approximate the expectation itself. Next, we approximate this entire quantity, and we particularly replace the empirical capacity, okay, with something else. And we remove basically the expectation. Now, how do we do this? Perhaps this is understandable, and I can show you some elements of this argument here. So let us prove the second lemma. Okay. So this is an expectation. The only randomness in here is over this particular term here, which is an empirical capacity term, an average over all the capacities indexed by the state S. Okay. So this is the statement that we want to show. Recall that this is the empirical capacity. Okay, capacity indexed by different channels. Now, furthermore, this part here, all right, this expectation, this should be capital SI, It's capital, right? Yeah. So this expectation is exactly the capacity term, okay? This is an expectation over the state, and we are averaging over all the different capacities. This will give me exactly the capacity term. Now, so we can basically replace this empirical capacity term with a bunch of independent random variables, okay? So by some massaging, we can basically replace the empirical capacity term with a bunch of independent random variables EI, where this J here is basically a normalized sum of the EIs, and EIs are basically related to the capacities. Each EI is a independent and identically distributed random variable with zero mean. The mean of this is that, and unit variance because I normalized appropriately. So I've reduced the problem to an expectation of some phi function where the random variable in there is some random variable that converges in distribution to a zero mean unit variance Gaussian. So Jn here converges in distribution by the central limit theorem to a zero mean unit variance Gaussian. So these are ID, Jn converges to normal 0, 1. So observe here, there is a Gaussian in here, there is an expectation in here. So we make use at the very end of the fact that the convolution of two independent Gaussians, the convolution of the PDFs of two independent Gaussians is a Gaussian where the means add and the variances add. And that's how we get the variances add up here. Now, once we have done this, we equate this to epsilon and we solve some equation and we will recover the asymptotic expansion. So here we need to play some games in that we need to introduce a bunch of independent random variables and apply central limit theorem a number of times, okay? And here we need to draw on some of the tools that we learned in an introductory probability class that the convolution of two Gaussian PDFs is a Gaussian. So that's the end of the story. Okay, so these are some new techniques that, these are some tools that we have to use in order to solve this problem where the state is available at both the encoder and the decoder. And for more details, of course, you can refer to the paper or better still, I think this is section 2 of my monograph. Okay, so that actually gives you a flavor of a problem in multi-terminal information, the first problem in multi-terminal information theory that is easy for me to describe. I want to go into two problems in which we have multiple rates, okay? There's a rate R1 and there's a rate R2. So now how do we talk about, how should we define the second order asymptotic or second order coding rates for such problems with multiple rates, okay? So right up to now, we have been dealing with problems with only one rate. We were interested in the asymptotic expansion for log m star, and we were interested in the backoff from capacity. What if we have multiple rates, R1, R2, R3, and so on and so forth? Now, it's not so obvious what is the meaning of backoff. Where are we backing off from? What is the fundamental limit? And the best illustration for this is actually the Slepin-Wolf theorem, in which we know the exact second asymptotics. Okay? So, just so we are all on the same page, what is the Slepin-Wolf problem? This is a problem of distributed lossless source compression. We have sources x1n, x2n, and we would like to compress them to messages m1, m2. This has nr1 bits, nr2 bits, and we would like to reconstruct them almost losslessly at the decoder. So this is a very famous problem. There are two correlated sources distributed according to some joint distribution, and there are n copies of them. They are separately encoded, and this is what's cool. Okay, separately means the two encoders do not talk to each other. And both are to be decoded as the destination. So the sources are to be compressed to nr1 bits and nr2 bits in the usual case. Okay, and we want to ask what is the minimum R1 and R2 that we can tolerate in order to drive the error probability to 0. Now, this problem is ill-posed because what is the minimum of two numbers? Minimum of, a bunch of things. So we want to obtain a region of rate pairs such that almost lossless reconstruction is possible. Okay. So in particular, just to be precise, we say that R1, R2 are achievable if there exists a sequence of codes sizes 2 to the nr1, 2 to the nr2, and a block length n codes for which the error probability tends to 0. Okay. And we denote by script R, pxy, as a set of all possible achievable pairs, rate pairs. Okay, so these two gentlemen, Slepian and Wolf, proved that the region of all achievable rates is the following. Okay, R1 has to be larger than the condition entropy of given x2. R2 has to be larger than the condition entropy of given x1. And R1 plus R2 has to be larger than or equal to the joint entropy. And this is really surprising at the time. Okay, really, really surprising, because you can do as well as the two encoders talking to each other. Really surprising. Okay, and so that's the region. That's the region of all possible achievable rates. And here I have used some simplified notation. H1 basically means the entropy of x1. H1 given 2 means the entropy of x1 given x2. So that's the region. And I think that some of you might have seen the Slepian-Wolf theorem, and so this is basically just a refresher. Okay. So here is the proof idea, which I probably won't go through. Okay. So in traditional Slepian-Wolf coding, okay, in traditional Slepian-Wolf coding, we choose the number of messages M1 to be 2 to the NR, number of messages M2 to be 2 to the NR, and we seek the optimum rate region. We sort rates R1 and R2 to drive the error probability to 0. The essence of my talk is not to drive error probabilities to 0, but to consider the scenario where the error probabilities are bounded above by some epsilon. And this is motivated by, considerations for finite block length where we really cannot drive things to 0. Okay, so the essence of second order analysis for network problems is the following. We can fix R1 star and R2 star, this is a pair of rates, on the boundary of the optimum rate region. Fix a pair of rates on the boundary of the rate region. I will draw a picture later on. And a permissible non-vanishing error epsilon. And we choose, instead of e to the, or 2 to the nr1, 2 to the nr2, we choose the number of messages to be 2 to the nr1 plus root n L1, 2 to the nr2 plus root n L2. Okay, so this is slightly different from above. And we seek the L1, L2 pairs. These are called second order coding rate pairs, such that the lim sup of the probability of error is no larger than epsilon. So we allow the error probability to be non-vanishing by epsilon asymptotically, but the number of messages is not exactly look like that, but it's just like generalization. Okay, so we are allowed to deviate a little bit from the fundamental limit, from a fundamental limit. Okay, so let me try to illustrate this. Okay, so this is the boundary of the Slepian-Wolf region, this pentagonal part here, and there are many boundary points, uncountably many. This is one point. This corner point is quite interesting. We'll talk about that shortly. This point is also another point of interest. This is a corner point. So we can fix R1 star and R2 star, center our analysis anywhere on the boundary of the capacity or the optimum rate region. And we can then ask for the deviations L1, L2 from that boundary point and find the region of L1 and L2, okay, for which the asymptotic error probability is no larger than epsilon. Okay? Exactly, I've just repeated exactly all these points here. Okay, just to be a little bit more formal, we say that L1 and L2, these are called second order coding rate pairs. Okay, they are exactly analogous to the back-off terms in what I've talked about for point-to-point source and channel coding. L1 L2 is R1 star R2 star achievable. So now we are parameterizing the second order coding rate pairs. By the point we are centering our analysis at R1 star R2 star, we are also considering a fixed error probability epsilon. We say that L1 and L2 are achievable, R1 star R2 star epsilon achievable if there exists a sequence of codes, okay, for which these two conditions hold. Basically, that the size of the messages behaves as nr1 star plus root n L1, okay, and m log of m2n behaves as n of r2 star plus root n L2. And the asymptotic error probability does not exceed epsilon. Okay, so this is exactly what I talked about a few slides ago. This may be a little bit hard to parse, but all you have to think of is that M1 behaves as 2 to the nr1 star plus root n L1 and so on, so forth for the other terminal. Okay, so we just like in Slepian-Wolf coding, there are two rates. Here there are two second order rates. So it does not make sense to talk about minimizing anything, all right? So we have to talk about the region, but now it's a region of second order coding rate pairs. Second order coding rate pairs. Centering our analysis at R1 star, R2 star, any arbitrary point on the boundary of the Slepen-Wolf region. So this is a result I will announce here, are published, our joint work with Oliver Kossuth, and published last year. So I want to revisit lossless source coding and allow you to see a connection between this definition and the asymptotic expansions that we saw previously. Recall that previously we proved through a sequence of steps involving hypothesis testing that the minimum number of code words, or minimum number of reconstruction points, okay, for a discrete memoryless source with error probability epsilon is given exactly by the following, right? We proved this carefully. So in a slightly different language, I can define L, which is a real number, can be positive or negative, to be HP, okay? This plays the role of the point on the boundary of the capacity region. Note that H of X or H of P, the entropy, is the phase transition between what's possible and what's not. So that is H of P epsilon achievable if there exists a sequence of n, mn epsilon codes such that the asymptotic error probability does not exceed epsilon, and the total number of reconstruction points scales as n multiplied by the entropy plus a square root n term whose coefficient is L. And we seek the smallest possible L, okay, that is epsilon achievable. All right, we seek the smallest possible L. And what is this smallest possible L? Well, if you basically wrap this around and you move the n h of p to the left-hand side, divide both sides by root n, you see that the L term is basically this guy here without the n. So the optimum second order coding rate for source coding is exactly this. So what are the definitions that we have developed are exactly analogous to this, except that in the Slepen-Wolf problem, we have two rates, okay, R1 and R2. We have two rates. So we need to talk about a region of second order coding rates. So this is a bit hard to wrap your head around, but just think about regular Slepen-Wolf. In regular Slepen-Wolf, we have two rates and we need to worry about a region. Now we fix a point on the boundary of the capacity or the rate region, optimum rate region, and we need to talk about two deviations away from R1 star and R2 star, which are given by L1 and L2. Okay? Any questions? Okay, so just to illustrate the point, all right? So here, maybe I'll skip this. This is not so important, okay? And let us consider the following, okay? So let me just go back to the two encoder case, and let's try to solve this problem, okay? Let's try to find the optimum rate region, optimum second order coding rate region, all right? So we have various points we can center our analyses. So here, R1 star and R2 star, okay, is on the vertical boundary. It's on the vertical boundary. Now there are 5 distinct cases. You're either on the vertical boundary, you're either on the horizontal boundary, you are on the dominant phase, or you are at the corner points. 5 possibilities. Okay, the results will be partitioned into these 5 different cases. And I will consider one of the simplest cases. You are strictly on the vertical boundary. What happens? Okay, now suppose that now R1 star is h of x1 given x2, so that is R1 star, and R2 star is h of x2 plus delta, for some delta greater than 0. Okay, so we are strictly above this corner point. What happens? What is the rate region? What is the second order coding rate region? Here's the claim. The second order coding rate region consists of all pairs L1 and L2, not necessarily positive. Okay, so they can be arbitrary numbers on the real plane. Okay, such that L1 is greater than or equal to the conditional dispersion of the source of x1 given x2, phi inverse of 1 minus epsilon. This phi inverse of 1 minus epsilon is exactly minus phi inverse epsilon. There are many different ways of writing it, or q inverse epsilon. Okay, so this is the same as lossless source coding with full decoder site information. All right. Note that there are no constraints on L2. L2 can be any real number. Okay. Now, what is the intuition here? What is the one-line proof here? Okay. Actually, we need more than one line. Okay. what is the intuition here? The intuition here is that the rate of the second source is strictly above the entropy, delta above the entropy, which means that we can compress very reliably. In fact, the probability of error of estimating the second source decays exponentially fast by traditional exponent analysis. So I do not care what the exponent is. It is some positive number dependent on delta, our deviation away from an entropy. So because this probability decays exponentially fast, it does not affect the second order asymptotics. All that matters is the first source. And the first source, okay, is right at the boundary here, is right at the boundary of h1, hx1 given x2, okay? And so we need to consider its deviations away from the fundamental limit, okay? And those deviations are given exactly like in the source coding scenario. There is a term known as, here we have to consider the conditional dispersion term, which can be defined very similarly to just the regular dispersion, and a Q inverse or phi inverse term. This can be written as minus phi inverse epsilon, as I mentioned. So that's not very difficult. Now here is another scenario. So we have to run through the sequence of, run through 5 cases, but 2 of the cases are repeats of the other, so I will omit them. So here we are on the dominant phase, strictly on the dominant phase. We are not touching any of the corner points. And so here, R1, just to write it more formally, R1 is sandwiched in between h of x1 given x2 and h of x1. We assume that the mutual information is positive so that R1 star exists. Okay, otherwise we cannot find R1 star that is sandwiched between the two. And we are lying on the dominant phase, so R1 star plus R2 star is equal to h of x1 and x2. All right, we are right there. Okay, so what is the second order coding rate region? Well, now the second order coding rate region simply depends on the sum of the L1 and L2, so the deviations away from R1 star and R2 star. And that is exactly the joint dispersion of the sources, the joint bar entropy, if you may. So that's the variance of the log of 1 over P of x1, x2. Okay, so this is the same, exactly the same as lossless source coding with the joint source x1, x2. Think of the source x1, x2 as a big source with alphabet script x1 multiplied by script x2. Okay, same, exactly the same. All right, you can think of this as again minus phi inverse epsilon. The intuition here is that both marginal rates R1 and R2 are strictly above h of x1 given x2 and h of x2 given x1, so they can be reliably recovered. Exponential, there's exponential reliability. The probability of error decays exponentially fast, so we are fine in terms of second order asymptotics. So more precisely, what we will have is the following. All right, we can develop finite or non-asymptotic bounds for the Slepin-Wolf problem, and this goes back to 2 Japanese information theorists, Miyake and Kanaya. And I will show you a simple proof. Let us try to prove, okay, in some sense. Case 2. So the optimum error probability is roughly the probability that one of these 3 events happens. Okay, this is the probability. This event is the event that the log of the basically the information variable or the conditional information variable is at least 1 over n log m1. m1 is the total number of reconstruction points for source 1. And this is the same for source 2. Here is the joint scenario. Okay, so roughly speaking, the optimal error probability is the probability that either one of these 3 events happens. Okay, so this requires a converse proof and an achievability proof that I will not show here. So now we are going to set log of m1n to be the following and log of m2n to be the following. Okay, we can certainly do this, and log of m1n, m2n to be the following. Okay, so now in this particular scenario, as you can see, the expectation of the log, the minus log of x1 given x2 is exactly conditional entropy. So the probability of the first event here, let us try to evaluate. The probability of the first event is minus 1 over n log of this information random variable greater than h of x1 given x2 plus delta. Okay. Now, this is a memoryless source, so we can decompose this into a bunch of independent random variables. Now, the mean of this is exactly equal to h1 given x2, hx1 given x2. And so, let's ask for the probability of this particular event. Well, you're asking for the probability that a normalized sum of independent and identically distributed random variables exceeding its mean by a small amount, well, that decays exponentially fast by some simple theory of large deviations. Okay, and we can actually bound this more carefully, but we don't have to, right? And this doesn't work anymore. Okay. Okay. Okay, this also doesn't work anymore. It suddenly stopped.
Huh,
or maybe this hung. So the point here is that the probability of E1 as well as the probability of E2 decay exponentially fast. So the only probability that we have to care about is that of the joint event. Okay? Okay, thanks a lot. So we are only left with the probability of the joint event, which is exactly this probability, again, because the source is discrete, is stationary and memoryless. So this becomes a sequence of IID random variables, and with some simple massaging and the central limit theorem, we see that the left-hand side converges to a zero mean Gaussian with variance 1. So comparing that to phi inverse epsilon, we get exactly epsilon. The last step follows exactly from the central limit theorem. And the main point here is that probability of E1 and probability of E2 are exponentially small. So they do not affect the second order behavior. And only the joint event affects the local second order behavior. So we are only left with one last case. Okay, the case of the corner point, which is perhaps the most interesting and requires some new techniques. Not exactly new, but some thinking, all right? So here we are. This is case 3, the corner point. So suppose now that R1 star and R2 star are conditional entropy and h of x, the marginal entropy h of x2, i.e. we are near the corner point. Okay, we are really at the corner point in terms of rate. Okay, so this little theorem here specifies what the optimum second order rate region is. Well, we are looking at all possible pairs of L1 and L2 for which this equation holds. All right, what is this inequality saying? Well, first and foremost, this is the generalization of the phi function of the cumulative distribution function of a Gaussian. So this is exactly the cumulative distribution in multiple dimensions. And this is parameterized by some mean and some variance. And the covariance here is exactly given by the covariance of these 3 random variables, but only restricted to the first component and the third component. Okay? Now you'll see how this mess comes about. This looks very messy, but actually the ideas are really simple. Okay? So again, we start from these non-asymptotic bounds involving 3 error events. And let us see. Since we are far away from the second rate constraint, okay? So that is the second rate constraint. We are far away from it, okay? Since we are far away from the second rate constraint, the probability of a second event again tends to 0 exponentially fast. We have done this exercise before, okay? So now, what we are left with, essentially, we can drop the second event since the complement decays exponentially fast. We consider the complementary probability, that is 1 minus epsilon n. And we see that that is probability of E1 complement by just simply taking the complement of this event here. This is the probability of the complement of E1 intersect the complement of E12. So this is the intersection of 2 events, right? And we can write this very simply as the random vector here being less than, pointwise less than these rates here. Okay? By this notation, I mean that the first component is less than that, the second component is also less than that. So this is an n, all right? This is the usual generalized, right? Okay, with respect to the non-negative Orton, whatever. Okay, so again, we set log of M1 to be this, and log of M2 to be that, all right? So that is the conditional entropy, that's the joint entropy, and these are the deviations, all right? So now again, we assume that the first order rates, as I mentioned, are really at the corner point, conditional entropy as well as entropy. And what do we have here? Now we can simply rearrange the following. We can plug these into here and rearrange and do a little bit of massaging. Okay, we move all the entropies to one side and we see that this is actually a zero mean random vector. This zero mean random vector appropriately normalized. So what does this converge to by the central limit theorem? In fact, we need a so-called multi-dimensional central limit theorem. Okay, So the multi-dimensional central limit theorem basically says that this bunch of normalized random variables converges in distribution to a normal random variable with zero mean and an appropriate covariance matrix. Okay. Now we plug this into, so this is a, so we can apply the central limit theorem to this object here, but now we have two. We have to apply the multi-dimensional central limit theorem. Okay. And in fact, 1 minus epsilon here can be compared to the probability, okay, that L1 exceeds this quantity and L1 plus L2 exceeds that quantity, okay? We can basically replace this by a Gaussian random variable with the correct covariance matrix, okay? So the punchline here is that once we have two rates, we have to consider the region, the first order region of conditional of entropies, okay, for the Slepin roof problem, center our analysis at the at an appropriate point, and in the case where we have corner points, we need to be very careful. We probably have to use a multi-dimensional central limit theorem to determine what this guy converges to. Okay, what this guy converges to. Usually, it converges to some Gaussian with some mean and some variance, some mean and some covariance, and to apply that accordingly to bound error probabilities. Okay, so that's the punchline, and I'll just summarize this here again. So the whole point is to focus on cases in which the rate constraints are active. For example, if we are at the corner point, there are two rate constraints that are active, the marginal rate constraint and the sum rate constraint. If we are only at on the vertical boundary, then only one constraint is active and you only need the scalar central limit theorem. If you are at the corner point, two constraints are active and you need a multi-dimensional version of the central limit theorem. That's what this slide is talking about. Okay. So now once you have multi-dimensional central limit theorems, then the region looks kind of strange, but it is a region and you can plot it in MATLAB. And so this is probably the first time you are seeing this sort of expansions for situations where there are multiple rates, okay? Situations where there are multiple rates and we have to deal with the analysis in a very careful way, okay? Depending on where we are centering our analyses at. Yep?
So for multi-dimensional SE, what's the dependence on dimensionality?
Oh, there is a paper on the dependence of the multi-dimensional central limit theorem. And dependence on dimension is d to the 1/4. D is the dimension of the problem. The remainder term is proportional, of course, to root n, 1 over root n, and the dependence on the dimension is d to the 1/4. Multiplicative d to the 1/4. Yeah. So the dependence on the dimension is surprisingly not very severe. Huh? Okay, 1/4 is not bad. Okay. Okay, I have about 18 minutes left, and I want to talk about the last topic. All right, there is really not so much math in here in the last topic. The results are nice and clean, and just give you an intuition for when we can further generalize some of these ideas. Okay, so this is the Gaussian interference channel with strictly very strong interference, and I'll tell you exactly what I mean. Okay, well, we know what is the Gaussian interference channel, hopefully. All right, so you have two independent messages, two independent encoders, and you want to transmit messages M1 and M2, you encode them to code words X1 and X2N, you pass them through a Gaussian interference channel, so you add some noise, okay, to this, and you obtain Y1 and Y2N, and the phi's are the decoder. You want to estimate messages M1 and M2. Okay, so that's exactly the channel transition from X to Y. Okay, so there are some gains here, and there are some independent noises. In the Gaussian case, which is what about now, all right, we somehow need to limit the powers. So I will consider a so-called peak power constraint. All the code words have to satisfy the peak power constraint. That is, their L2 norms have to be less than or equal to Sj. Okay, S1 or S2 depending on the transmitter. Okay, so these S's are constant. They are numbers. They are positive numbers. Okay, so the capacity region, for general G's, is an open problem. Okay, in network information theory, although there are some nice bounds and some capacity approximations. All right. So for this problem, we can define 4 numbers. two signal-to-noise ratios and two interference-to-noise ratios. In a very natural way, the signal-to-noise ratios are basically the channel gain squared power and channel gain squared power. All right, so these G11 and G12 are the direct links from encoder 1 to decoder 1, right? And these are the cross gains, okay? So we can also define the so-called interference-to-noise ratios, two of them. All right, these are very natural things to define. And then if the SNRs and the INRs satisfy some nice relationship, we know the capacity region in some very special cases. For example, in the very strong interference regime, right? This means that the signal-to-noise ratios are small compared to the interference-to-noise ratios in this fashion here. So the signal-to-noise ratio 1 is smaller than interference-to-noise ratio 2 divided by 1 plus signal-to-noise ratio 2. And replace the 1s with 2s and 2s with 1s. So this is the so-called very strong interference regime. And in the strictly very strong interference regime, we replace the inequalities, the non-inequalities with strict inequalities in this way. And equivalently, we can write these conditions in terms of the capacities of the AWGN channel, which is half 1 plus S. Okay, so the sum of the capacities evaluated at the SNRs are less than the minimum of these capacities. Okay, so that is the so-called very strong interference regime. Okay, so in this case, life is easy, and the problem decouples into two independent problems, in some sense. Okay, and I'll show you why it decouples. Intuition is that receiver 1 can decode the interference and then subtract the code word associated to M2 and then use that remaining signal to decode message M1 and vice versa. And because of the strictly very strong interference, the more stringent condition is on decoding M1 and not on So in fact, the Gaussian interference channel now behaves as two independent channels, two independent point-to-point Gaussian channels. Okay? So this is the capacity region. And this is the gentleman who proved it in 1975. Okay? So the capacity region is basically a rectangle. All rates in this box are achievable. All rates outside the box are not achievable. And we want to examine what happens on the boundary, just as in the Slepin-Wolf problem. Okay? So again, there are three distinct points here: vertical boundary, horizontal boundary, and corner point. There are three distinct points here. And Carlisle showed that the capacity region is that, where C1 is the capacity of the direct link from the first encoder to the second encoder. So this is the capacity in terms of SNR1. And the second link is the second constraint is basically that R2 is less than the capacity of the second channel. Okay? And SNR2 is basically G22 squared multiplied by the permissible power for the second transmitter S2. So our job here is to examine deviations of order 1 over root n away from the boundary. And again, there are three distinct regions of the capacity region. Okay, vertical boundary, horizontal boundary, and corner point. And of course, as you can expect, the corner point is the most interesting. Okay, so I probably won't go through Carlisle's proof, which is just very simple. Okay, but again, how will we set up this problem of examining deviations of order 1 over root n away from the boundary? Well, we will define L1 and L2 to be, again, epsilon R1 star R2 star achievable if there exists a sequence of codes, okay, for which the message sizes scales as the following, and the optimum error probabilities do not exceed epsilon asymptotically. Okay, so another interpretation is that if L1, L2 is achievable, fixing the corner point, fixing some point on the boundary and some error probability, then there exists a sequence of codes for which the message sizes in the first order term scale as R1 star, and in the second order term scale as root n L1 or L2. Okay, and we want to examine what is the set of all possible epsilon R1 star R2 star achievable second order coding rate pairs, i.e. these L's. Okay, so we want to go after this set L epsilon R1 star R2 star. okay, for the Gaussian interference channel under this specific regime in which we know the capacity region. Other regimes, I don't know. Now, note that in the single user case, we can evaluate this expression, we can evaluate the optimum second order coding rate, that is the maximum second order coding rate, pretty efficiently. We know how to do that. And we can evaluate the dispersion as well using techniques very similar to the discrete membreless case. And it's given by this simple expression in terms of the SNR. Okay, in the single user case, there's only one SNR. We don't even have to talk about the channel gain, right? So this is joint work with my student Lacey Kwok, as well as my colleague Mehu Motani. And for the details, you can look at this paper. Okay, so what we did was to characterize this following second order coding rate set for all possible values of epsilon and all possible R1 star and R2 stars on the boundary of the capacity region. Okay, I will not talk about this. Okay, so there are, as I mentioned, three distinct cases: vertical boundary, horizontal boundary, and corner point. Now, in the vertical boundary case, what do you think we can expect, right? So the error, because we are strictly below the capacity of the second user, so the error event for the second error probability of decoding the second message should decay exponentially fast. No problem with decoding the second message. Okay? So the only problem is that decoding of the first message may be problematic. You may have a non-vanishing error for the first message. So the second order asymptotics only pertains to user 1. And the second order coding rate cannot exceed, for user 1, cannot exceed the usual quantity. Square root dispersion, phi inverse epsilon. So the second user doesn't come into play at all. Okay, this set here is independent of L2. L2 can be any real number. So that's nice. That's simple. Okay, we do not really have to examine the horizontal boundary because that's completely symmetric, right? So here, what we're after, and this is probably the last result that I will present, is the corner point, the third. The case tree, okay, corner point. In this case, we are here, both boundaries. And it turns out that what we can prove, and this requires some effort, okay, the L1, L2 pairs in the optimum second order coding rate region consists of the a term related to the decoding of message 1, a term related to decoding of message 2, and we relate that to 1 minus epsilon. Let us try to gain some intuition for this problem, for this solution, okay? Let's try to gain some intuition. And this is just a plot. So I won't go through the plot. Let us give a heuristic definition or heuristic derivation of case 3. Now, let me define the event Gj to be the event that message J is decoded correctly, all right? Now, from everything that we have learned, okay, the probability that you decode correctly, so let Gj be the event that message J is decoded correctly. We want both messages to be decoded correctly, so we want to consider the probability that the intersection of these two events is larger than 1 minus epsilon. So the error probability is smaller than more than epsilon. Okay. Now, because the channel looks like it's going to be, looks as if it consists of two independent channels, let us assume for the moment that these two events are independent, although they are not. All right? This is the whole generally. Let's just do some bad math, and let's just assume that this product, this intersection of events can be decomposed into the product of these two probabilities. This is really bad math. But this gives us some insight, all right? What is the optimum error probability? What is the probability that you can correctly decode? Well, we have learned this. We have seen from the single user case that this exactly, the error probability is exactly phi of L1 or L2 divided by the square root of the dispersion. This is something I talked about at the very beginning. So the probability of the correct decoding is 1 minus that, which is exactly phi of minus Lj divided by Vj. So putting these two together, we get this result. Of course, this is a very heuristic definition because the events G1 and G2 are not independent in general. But it turns out that they are almost independent. We can quantify what almost independent means to obtain the final result. So it looks as if the two channels are operating independently. Okay, so this is the probability of correct decoding of the first channel, first message. This is the probability of correct decoding of the second message. So the product looks as if, you know, the probability of correctly decoding both messages equate that to be larger than or equal to 1 minus epsilon, and that turns out to be the optimum region. So there is no interaction even in the second order sense. So that was a little bit surprising to us. Okay, so converse requires generalized Hayashi-Nagaoka. So Carlisle mentioned in the conclusion of in his paper that very strong interference is as innocuous as no interference at all. Okay, because we can easily subtract the interference, and the limiting condition is actually the decoding of the intended message. Okay, now it turns out that under the strictly very strong interference condition, so if the inequalities prescribed by Carlisle are strict, we see that the dispersions are unchanged as well, and the two channels behave really as if they are independent. Okay, we need this strict condition. We need this strict condition for the achievability part, not for the converse part. It doesn't seem like other classes of interference channels are amenable to second order asymptotic evaluations. So as I mentioned, the error events look approximately independent, which is nice. So the intuition is that the Gaussian interference channel with very strong interference looks as if it is analogous to two independent direct channels, even in the final second order sense. Okay, so those are all the technical things I want to talk about, and in the last, I don't think I have about 4 minutes left. I want to talk about a few, I want to summarize, and I want to talk about a few open problems, okay? Actually, everything is open. Everything is open. So we saw that binary hypothesis testing results can be used for lossless source coding, okay? And these are the two results that we derived. Okay, binary hypothesis testing, we were concerned with beta 1 minus epsilon or product measures. And in source coding, we were concerned with the minimum code size for a source P with error probability epsilon. And we derived these two expansions. And in channel coding, we spent a lot of effort trying to derive this particular expansion. And we saw that Feinstein and Hayashi-Nagaoka are good enough. Okay? And for channels with state, we saw that in general, you have a dispersion term that splits into two parts: randomness of channels, randomness of states. Okay? And in the Slepin-Wolf problem, we saw that we need to use in general, we need to use a multi-dimensional central limit theorem. And for the Gaussian interference channel with strictly very strong interference, at the corner point, it still seems as though we are operating with two independent channels. Okay, even in the final second order asymptotic sense. Okay, so some open problems, some very natural, very simple open problems. Well, you flip to any page of Al Gamal and Kim's book, there is a multi-terminal problem, and you can analyze that in the second order sense. The question is whether you can get anything tight. And most of the time, the answer is no. So here is a natural problem, all right? Here we are only interested to estimate one source, and so this is very much like the Slepin-Wolf problem. This is called lossless source coding with coded site information. And the first order rate region is known, and in fact also the so-called strong converse. It's not so easy to derive the strong converse though. So here we are interested in reproducing only one source. We compress both sources. We are only interested in the X source. Okay, so the rate region is known exactly. This is due to Weiner, Elswedy, and Connor. The strong converse is known. It's not very easy to prove that. So we can try to do second order analysis for this, but we only have good inner bounds for the second order rate region. So this is the so-called problem. I talked about the situation where the state is available at the decoder and at the encoder and the decoder. Here, the state is only available at the encoder, and that causes a big headache. All right, and we haven't been able to do this. So again, the capacity is shown right here. Okay, and this is the so-called Weiner-Ziff problem. This is a lossy source coding problem where you are interested to compress one source here and reproduce it up to some distortion at the decoder. And the rate distortion function is very well known. It goes back to Weiner and Ziff 1976. All right. So all these three problems are site information problems. And the problem with these analysis is that the presence of the so-called auxiliary random variable U makes the converse part very intractable, and I do not know how to do this. The best achievability results are due to myself, Shun Watanabe, and Shigeki Kozuoka, as well as an Iranian group consisting of Yazai, RF, and Gohari. Those are the best non-asymptotic achievability bounds, but no one has come up with any meaningful converse bounds at the present moment, except for the Gelfand-Pinsker problem in the Gaussian case, dirty paper coding, that we know the dispersion exactly. Okay, the idea of myself, Watanabe, and Kozuoka is a channel resolvability, a concept that goes back to Han Verdu, all right? I have no time to talk about that here. The concept, the idea in Yazai, RF, and Gohari is the so-called stochastic likelihood encoder and stochastic likelihood decoder, okay? So there are many other open problems like for which we know the capacity region, like degraded broadcast channel or the Gaussian version. Degraded broadcast channel is another problem. We know exactly what the rate region is that, okay? But again, the presence of the auxiliary random variable does not allow us to do the converse part in an easy way, right? We know how to deal with auxiliary random variables in the converse part, okay? And of course, we also know the capacity, the exact capacity of the degraded channel. No problem. It is given by the cut set bound, okay? Now here, there is some hope. There is no auxiliary random variable. So for all the people who are enthusiastic in this topic, this might be a good start. Degraded relay channel, capacity is known, no auxiliary random variables, so there might be hope. And the Gaussian versions of the above problems may be easier as I have some experience in the Gaussian versions, and sometimes things become more tractable because there's more structure. So we can also talk about information theoretic security, and there are some works by some groups, very, very nice works by my collaborators Shun Watanabe and Masahito Hayashi, in which they derived the second order asymptotics for key agreement. But for the wiretap channel, it's not completely solved yet in the second order sense. So this brings me to the end of my tutorial. Hopefully I've given you some idea on second order asymptotics for classical, very, very old-fashioned problems like lossless source coding and channel coding, binary hypothesis testing. And I've also given you a flavor of my research, my recent research on multi-terminal generalizations of such problems, including slap-in-woof and some simple interference channels. So I really want to thank CSCIT for inviting me to speak at this school, very well organized school. And I look forward to questions from the audience later on during the poster session or during dinner tonight. So thank you very much for your kind attention. Yeah, sure.
All right. If there are questions, in the network setting, it seems like assuming the probability error is epsilon, but in some sense, because there are multiple messages, so you can assume that one is multidimensional as well.
You can also assume that so there are multiple probabilities.
Something new here, or it will be pretty much.
You can assume that there are multiple probabilities of error, like probability that M1 is not the same as the estimated M1, and a different probability of error assigned to the M2 version. Okay.
Right.
I think that is even more difficult because of some decoupling.
Another question about the framework is that it seems like you're assuming the second order term must be square root of n.
Yeah.
So in definition, you're assuming that the second order term is normalized by square root of n.
Yeah.
Motivation or justification for that. It seems like you know some part of the answer. So you define your answer to be only, and it's even separable. I'm not sure whether the dependency on n and dependency on probability error epsilon, why are they separable even? Why the second order term must be a product of square root of n and some function of epsilon?
It doesn't have to be. It doesn't have to be, but for these simple problems, it turns out that the answer, yes, we assume what the answer is a priori, and then we prove it, and then we set out the problem formally.
And finally, you can prove that's really the case.
Yes. So there are some instances in which this function here, there are some very exotic instances in which this function here is not phi. It is the cumulative distribution function of some other strange random variable.
Okay, but they're always separable, right?
Yeah, they're usually always separable into something that consists of error probability and something that measures the quality of your source or channel.
Is this a fact, or this is the observation we have, or no results or any justification for these?
No justification, at least not to the best of my knowledge. Yeah.
All right.
So you have actually made one very good point, that why do we assume that the backoff term is of the order root n as well? I think earlier on in your question, and that there's no reason for that also.
And also always
that's motivated by the central limit theorem, but central limit theorem is based on the fact that, you know, I have a bunch of independent random variables, they converge to Gaussian, but they do not converge to Gaussian. I mean, in some sense, in some other problems that I didn't describe.
And also for all terms after square root of n,
yep,
it always goes to 1 directly. No other terms.
No, that's not completely true. So yeah,
Not completely true.
Yeah, completely true. Yeah, so you could have other things like n to the 1/3.
N to the 1/3.
For example, I didn't talk about this, but there's this class of channels, discrete channels called exotic channels. All right, for which the second order term goes away, and the third order term here, the first term is of course capacity. The remainder term is of the order n to the 1/3. So it really depends on your on the exoticness of your source or channel. Yeah. First and foremost, they have to have zero dispersion, which I completely ignored in my talk just now. And it is really exotic that you can construct them, but they live on a measure zero set. Yeah.
So the reverse engineered term, for example, has zero dispersion.
Yes, they were. Yeah, they put together a BSC and a BEC and some strange combination that I don't fully understand. Yeah.
So the interference channel, you said that the probability of best detections approximately independent, and that helped you.
Oh no, they are not independent.
Approximately.
They turn out to be approximately independent.
So does the same same sense of independence carry over to the weak interference regime, where weak interference as noise achieves the subcapacity?
I don't know that may be a good open problem. I do not know enough of interference channels to answer that question well. All right, so that may be another open problem that I didn't state. Yeah, we only have looked at the very strong interference setting for interference channels. Other channels, other settings, I do not know yet.
So it's like the other
Other extreme. Yeah, maybe. Yeah, I don't know. Now, once we have some rates, things become a little bit difficult, especially for the converse part. We need to play more games. Once we have some rates in channel coding problems. Well, in the Slepinov problem, we also had a slum rate, but things were relatively easy. Once we have some rates in channel coding problems, we have to use a technique known as ringing to establish something called the strong converse. So that is something that is hard to understand. Without that, it is impossible to establish a strong converse. It is impossible to second order results. Yeah. Yes, for the Mac as well. Yes, for the Mac. Yeah, so that there may be some hope. But we yeah. Dual. Yeah. But there are some problems which we can discuss offline. So it looks straightforward because the Gaussian Mac region is exactly a pentagon, but there are some formidable challenges, especially in the converse part. Yeah.
Any last question? All right. Yeah, let's really thank you.
Oh, thank you very much, Sid.
You're going to look surprised, right? Thanks, Vincent, for in fact volunteering to speak for 4 hours. He's like, 3 hours is not enough. The ideas are big enough to require a larger palette, right? Just like Naveen's talk. So thank you, and also for to use the whiteboard. I mean, it takes a certain amount of effort and clarity of thought to try to spell it out at a pace that captures people's attention. So we are running a little bit late. I prefer to think of it as we're running a little bit more in terms of better understanding rather than thinking of it as in terms of a schedule and so on. Schedules are meant to be tossed out of the window, right? So let's say that we'll take a 10-minute break now. Then we'll come back for the spotlight session, just like yesterday, spotlight session, and then we'll move straight to the poster session. Okay. Thanks, everyone. just like really such a part. Like I tried to hang around. I thought,
Oh, okay. I proved this.
I saw that. In fact, I took a look at the slides as well. But it looks like, well, I need to say more than that. I need to come, like, squeeze you dry. Because many of these things are things we're struggling with, and our own problems for other reasons entirely.
Yeah.
Even the student who's getting married today, he's like, oh, I want to see the first part of Vincent's talk before going and getting married. so then we also taxis over.
Okay. So hopefully it was okay.
I think it was pretty good.
Okay.
The only thing was like I think you were just so forceful. There were fewer questions when getting Naveen's talk.
Yes, that's right.
I think, but I think luckily the questions after.